All right. So the one question here that I think shows up on your review that we have not yet covered, the one topic is in Roman numeral 7 there, okay, where you have a linear equation and then a quadratic equation, okay, and it's a system, right? So you're solving to find the values of x and y that would solve both of those equations simultaneously, okay? So I'll just give us an example here of, sure. So, okay, so there's our system. Okay. We have a line, right? Y plus 3x. And we have a quadratic equation there. Y minus 6 equals negative 3x squared. Okay, so that's quadratic as well, you have x squared. Okay, so we're going to have a line and a parabola on a graph. Okay. Now, if you visualize a line and a parabola, right, and how those two things can interact. If we were to graph this, for example, that would be one way that we could solve the system, right? You could solve the system by graphing. And in order to graph these, what we need to do for both these equations? Yeah, we need to solve for y, right? So, in the first case, right, we can solve and just get y equals negative 3x, right? And in the second case, right, we would just add the 6 over, so we'd have y equals negative 3x squared plus 6, and we could graph this. All right, and so I'll show you with the graphing calculator. So there's the line, and then there's the parabola. Okay, I think I can zoom 6 there. I think I can standard viewing window. Okay, we can see our 2 points of intersection. Okay, so in this case, right, we're going to have two answers. Will a linear quadratic system? We just started, so will a linear quadratic system? Will it always have two solutions? Will it always have two solutions? Must the line intersect the parabola? Could it be that our line would never intersect the parabola? No. It could be, right? Imagine if I took this line and I shifted it up some more, so our y-intercept was like up here, it would never intersect. So in other words, how many solutions would that be if the line and parabola never intersected? 0 solutions, right? Okay. And it's also possible for the line to intersect the parabola at exactly 1 point as well. Okay, so with these linear quadratic systems, you're going to have either no solutions, right? It'll not work, right? It won't intersect, or one solution or two solutions. You will never have the infinite solutions, though, like you remember having when you had two lines, right? Sometimes there are situations where when we had two linear equations, you have an infinite number of solutions. Why would it be impossible for us to have an infinite number of solutions in a case like this? Any ideas? So, yeah, Max?
One is increasing linearly and the other is increasing exponentially.
Yeah, okay. So they're increasing at different rates, okay? These things would never completely overlap with each other. Remember that in a two-line system of equations, when you have the infinite option, the two lines are the exact same lines. Well, a line will never exactly match to a parabola. You might be like, well, if we go further down here, it looks pretty linear. And it does look pretty linear, but they're not the same. Okay, it's not the same. So these two things will never have, a linear quadratic system will never have infinite solutions. But it could have 2, it could have 1, it could have 0. And so to find these points of intersection, just press second trace and go down to the intersect command, right? Move your cursor close to one of the points of intersection and just hit enter, enter, enter. And there's our 1 point, negative 1, 3. Okay? And then same thing, intersect command, arrow down, arrow to the right to the other point intersection, enter, 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 and voila, to -6 is the other solution there. Okay? But what if we want to do this without a graphing calculator? How can we solve it? Well, elimination is not really an option here. Okay? Well, I guess it kind of is. You can limit the y's here. But the best way to go, I would say, if you're not going to use graphing, is to use substitution. If you don't want to use your graphing calculator, it's to use substitution. Okay? In this system, we have that y is the same as -3x. We also have that y is the same as -3x squared plus 6. These two y's in this system are describing the same y value. So we can set then -3x equal to -3x squared plus 6. Okay? So this is using substitution. So I guess I'll put option here, graph, and find points of intersection. Okay, graph and find points of intersection, or we could use substitution here. Okay. To continue solving this, what should we do? What would be a good next step in order to solve this new equation that we have with substitution? How should we go about solving this equation? Any ideas? What would be a good next step? Jill? Okay, move the 3x over. Christian, did you have your hand up too?
Yeah.
Is that what you're going to say? Move the 3x? Yep, perfect. Make it equal to 0, right? So -3x squared plus 3x plus 6, and that's equal to the 0 there. Okay. What would be a good step to do now? What would be a good next step now? So yeah, nice.
Quadratic formula.
Okay, you can use quadratic formula. That's one option here if you want to. Okay. You can also try using another strategy like factoring. Okay. In fact, I see right now, before we use quadratic formula, it might be a good idea, even before quadratic formula, to do what? To factor out what here?
Greatest common factor.
Yeah, GCF. Yeah. So Paige, what would you say to factor out here? Yeah, 3 or a -3. Okay, your choice, whichever one you want. I'm going to do a -3 just because I really don't like having a lead coefficient of -3, okay, or a negative number. So, in fact, I'm just going to divide both sides by -3 like this, because we do have an equation, so we can just divide it out. Okay, or you can also just factor out the GCF, however you want to think of it. So anyway, we get x squared minus x, and then minus 2. And then I think this does factor, or actually we know it factors because of the, but you could use quadratic formula too. Okay, it's going to factor to x minus 2 and x plus 1. Okay, and so we get x equals 2 and x equals -1 when we get our zeros there. Okay, but of course we're not done yet. What do I need to do with these x values? So we have x values. I need to get coordinates though, right? I want to know where these two things intersect. I have the x coordinates where they intersect. How can I figure out what the y coordinates are? Plug it back in. Does it matter which equation I plug it back into? It does not. So I'm going to use the top one because it's a lot easier, right, to do that math. So y equals -3 times 2. Y equals -3 times -1. So you get -6 and you get +3. So our final solutions are 2, -6, like we said from the graph, right, and -1, 3. Okay? And so those are our solutions to that system, which again we got from the graph too. You have that option as well. Okay? Question?
Can you put to the right a little bit?
Yep. Like this way?
Yeah.
Okay. And that's the only one I'm going to do for you guys because really that's pretty much it. Okay, that's pretty much all there is to it. Okay, it's just, either graph both, find the points to intersect if you have a graphing calculator, or you can use graph by hand if you want to, or you can use a substitution. Solve one for x or y, plug it into the other equation, and then simplify. I would always encourage you to solve for like the y's, especially if it's like the x that's being squared there. I'd say, solve one for y and then plug it in and go from there. Just put your x's. Okay. Questions on any of that? Yeah, Karina. Should be a positive. So like right here, you're saying?
No,
Here?
no, negative 1.
This right here? Should be a positive 1.
I got a positive 1.
No.
Negative 2.
Positive 1, negative 2. Interesting. Well, let's see here. So, okay. So add 3x over negative x squared plus 6. Divide everything by negative 3. It's positive x squared minus positive minus. Okay. Did I combine factors here? That factor's right. Negative 2 times 1, negative 2. Negative 2 plus 1 is negative 1. And that factor's right. And so then if x minus 2 is your factor, x equals 2, positive 2 would give you 0. Right? Yeah. I mean, if I have x minus 2, that's x minus 2 equals 0. And then if x plus 1 equals 0. So that means x is 2 when I add 2 to both sides, or x is negative 1 when I subtract 1 from both sides. All right? And so then you would plug those back in. Okay? And get your variables. So no, I think that's right. I think that's right. And again, I think that matches what we did for the graph, too. So. Right. Is that clear, Karina, now? Got it. And Max, you're okay too? Okay. All right, then the rest of the time is yours, okay? I will come around and help. The answer key is already posted, okay, with worked out solutions. All right, but if you have further questions, I'll be happy to answer them. Please, please, please. Couple like little notes here, right? Again, abide by whether it's non-calculator or calculator active, right? If you look at these first, Roman numeral 1 to Roman numeral 4, like, Mr. Wood, these are so easy with my graphing calculator. I'm like, okay, but you won't have a graphing calculator. Okay. Also, remember that tomorrow you will have 80 minutes, and that's it. Okay. So make sure you're not only able to do these, but you're able to do them with efficiency and quickly. You can't sit there and just stare at a problem for 5 or 10 minutes. That's going to harm your other work too. So, question. Oh, okay, sorry. Okay, and then you have a question too, Okay, all right there. So, yes, and you of course can move around and work with others if you want to.
Wait, I never got a paper.
Oh, okay.
Yeah, outside the one from Friday. So you click
Right. There you go. Thank you. There you go.
Hey, this isn't too bad.
So also, just so you know, there is a non-calculator section and a line in the calculator section on the back too. Yes. Yes. Sorry. Yeah.